Assalamu alaikum, dear students. Today, the lecture number 2 of week number 3. The topics we are going to cover in today's lectures are the mechanical and electronic pressure measuring devices and the related numericals, the topics we have previously covered and the topics we will cover today. So let's move on to the first topic, the mechanical and electronic pressure measuring devices. So what are the mechanical and electronic pressure measuring devices we use in the field that we commonly observed whenever we see our car and we go to the petrol pump station, whenever go see a pressure tank? So always we see a gauge which indicates the pressure of the fluid present in the tank. So let's see what are the type of pressure measuring devices and how they work. So what are the problem with the manometers and why we need mechanical and electronic pressure measuring devices? So manometers are not well suited for measuring very high pressure or the pressure that are rapidly changing with time. So we can understand because the manometers depend on the height of the column of the fluid. But if 100 bar or 50 bar, okay, so these pressures are very high pressure. So we do not have such fluid that can handle the height of the column of the fluid. So because of that we need another type of pressure measuring device that can handle such a high pressure, and also the fluid needs some time to adjust the height of the column, but in some area the fluctuation or the pressure are changes continuously or very rapidly. So because of that also we need a system that can observe or measure the pressure changes rapidly. So therefore numerous type of mechanical and electronic pressure measurement devices have been developed. So when the fluid acts on a elastic structure, the structure will deform. This deformation is related to the magnitude of the pressure. Okay, so here we are talking about the material. Okay, the elasticity of the metallic structure. So the pressure measuring device works on this principle in terms is termed as Bourdon gauge pressure. So there are two type of Bourdon gauge pressure. There are two type of Bourdon gauge. One is the C-type Bourdon gauge and one is the spiral type Bourdon gauge. The C-type Bourdon gauge normally use where the pressure is small or moderate, but if the pressure is very high then we use the spiral type Bourdon gauge. Now let's see how this Bourdon gauge works. You can see in the picture this is a C-shaped Bourdon gauge. This is a C, you can see. Okay, this is C-shaped tube. Let's see how it works. The essential mechanical component in this gauge is the hollow elastic curve tube, Bourdon tube, connected with the pressure source. So this is called the Bourdon hollow tube, made with a metallic, it is made with a metal. Okay, and it is connected with the pressure source. This is the pressure source. It is connected with some kind of tanks, pipes, or whatever is the source you want to measure its pressure, or the tire of the vehicle. Okay, so this is the Bourdon tube in a C shape. Okay, as the pressure in the Bourdon tube increases, the tube tends to straighten. The tube deformation is translated into the motion of pointer on the dial. So you see, whenever this hollow tube is going to pressurize, when the fluid will enter from this source and come to this C tube, what will happen? This tube will try to straighten, it will move up, it will move up. So when it will move up, this, because of this movement, there is a gear mechanism. Because of that, it will move up too. So when it will move up to, then the dial will also rotate, the dial will also move. Okay, because of that we can see the dial is moving in the gauge. Here is the gauge. Okay, as the pressure increases, the dial will move upward. As the pressure goes down, the dial will come down. This is the mechanism and how it works. When the pressure increases, this tube start straighten. Okay, because of this high pressure, because of the high pressure, then it start moving up. Okay, when we release the pressure, then this dial will started going down. So the Bourdon gauge must be calibrated so that the dial reading can directly read the pressure in psi or Pascal. So normally we calibrate the gauge at 0. Okay, and the gauges are designed to measure pressure in height of the column, in psi, in bar, in Pascal. We can see in the whenever you have a chance to see the pressure gauges. Okay, you can see in the market, or you can see on the tank, you will see a different measuring units. Okay, so after that we can convert depending on basically what what measuring units you needed. So you can buy from the market. Okay, so it is available in psi, it is available in Pascal, it is available in kilopascal, it is available in the market in bar. It's up to you in what unit you want it to. Okay, zero reading on the Bourdon gauge indicates the local atmospheric pressure. Since we are calling it a gauge pressure, so we know that the reference point for the gauge pressure is the atmospheric pressure, where we consider the atmospheric pressure is 0. Okay, not the atmospheric pressure 0, because the reference point is atmospheric point. We do not measure the gauge pressure from absolute 0. We measure the gauge pressure from the atmospheric pressure, and from there we start counting 0, 0.1, 0.2, 0.3 and so on. So that's why the zero reading on the Bourdon gauge indicates the local atmospheric pressure, or you can say this is one atmospheric pressure at this point if you are calling it absolute pressure. Okay, so absolute pressure here, you can say that. So let's move on. So the another type of pressure gauge, that is called a aneroid barometer. So how we have another device that help us to measure the atmospheric pressure, and such pressure gauge is called aneroid barometers. So how this barometer works? The barometer is another type of mechanical pressure gauge used to measure the atmospheric pressure. Okay, so how it works? The common aneroid barometer contains a hollow closed elastic element. That element is completely evacuated to nearly zero absolute pressure inside the element. So you can see this is the element, this is the elastic element. Okay, and from inside it is completely hollow, it is evacuated. Okay, there is almost zero absolute pressure inside. Okay, so what happens when the atmospheric pressure is high? When the atmospheric pressure is high, it compresses and its dials goes up. Okay, so when the atmospheric pressure low, it release, it expands and the dials go down. So this is how it works. You can see this is the high pressure. When the high pressure, it compresses this elastic element, okay, and how this dark black line, you can see this is the behavior when the pressure is very high. When the pressure is low, the red one, and the light line, this is indicating when the pressure is low, so this is going up. When it will go up, this line will move here and the dials will go down. So this is the way how these aneroid barometer gauges are works. Okay, so this is the mechanism for the low pressure, and this is the mechanism for the high pressure. So as the atmospheric pressure changes, the element deflects, and this motion is translated on attached calibrated dial. So let's move on to the another type, because these pressure gauges are basically the analog pressure gauge, okay, because you have to observe and translate and read the values, okay, from the gauges directly and convert it into the reading. But here we have many other type also that we use directly in the digital system, where we measure the pressure in the digital form. Okay, so for many application, the measured pressure is converted into an electrical output. Okay, so this type of pressure measurement devices is called pressure transducers. Okay, the pressure transducers continuously monitor change in pressure with time. Okay, basically it monitor, and you can observe the behavior of the system or the fluid, that how the system pressure is varying. Okay, so based on this pressure transducer, you can measure or record those values. So how it works? In one type of pressure transducer, the Bourdon tube is connected to a linear variable differential transformer, okay, LVDT, as shown in the figure. So this is a Bourdon gauge, okay, this is the Bourdon tube, and this is the pressure connection line, this is the input line, and then it's moved forward, and how it's compresses and expands. And there is a LVDT, there is a variable differential transformer, which measures the deflections and convert these deflections in the electrical output. Okay, so the pressure transducers continuously monitor change in pressure with time. In one type of pressure transducers, the Bourdon tube is connected to a linear variable differential transformer, which provides voltage signals. These voltage signals are digitalized and stored on a computer for further processing. Okay, so such type of pressure transducers are not that sensitive as we used in the to measure the pressure in the arterial blood pressure, which is relatively small and varies periodically. To measure the such small and frequently changing pressure, we use strain gauge pressure transducer. So what are the strain gauge pressure transducer? Because here, why we need this strain gauge pressure transducer? Due to the some disadvantage of the Bourdon tube pressure transducers. It only measure the static pressure, because as we have studied, we have a static pressure, we have a dynamic pressure. Okay, so it measures only the static pressure. Second, because of a large mass of a Bourdon tube, it cannot respond to rapid changes in pressure. Okay, because definitely this C tube has some inertia, it takes time, it needs some some pressure greater than its inertia to work. Okay, so and also it needs time to move because it has a mass. So to overcome such pressure, we introduces another type of pressure gauge, that is called a strain gauge pressure measurement transducer. This difficulty can be overcome using a strain gauge pressure transducer. A strain gauge pressure transducer has a thin elastic diaphragm. So this is the thin elastic diaphragm. From here, this part is connected with the pressure side, the side you want to measure the pressure. Okay, we insert in the pipe, or we insert whatever is the source you want to measure the pressure. The pressure exerted on this diaphragm here. Okay, so strain gauge pressure transducer has a thin elastic diaphragm used as a sensing element. So this is the sensing element. Okay, the diaphragm is in contact to the fluid. So whatever is the fluid, air, water, oil, or whatever it is, or blood, whatever it is connected, this diaphragm is in direct contact with the fluid. As the fluid pressure changes, the diaphragm deflects and passes a voltage signal to the computer. So as it deflects, so there is a movable armature. Okay, it moves, and then there is a strain sensitive wires. They contract and then they expand according to the movement of this armature, and from here they transfer signal to the wire and then to the computer. So this type of pressure transducer can be used to measure both small and large pressure, as well as static and dynamic pressure. You can read in detail, or you can view some of the videos in the YouTube channel and see how these pressure gauges works. The Bourdon gauge, C-type Bourdon gauge, spiral type Bourdon gauge, YouTube manometers, and the previously we have studied the aneroid barometer. Okay, and strain gauge barometer, all we can study. So now let's move on to the second topic today, the problems. The topics we have studied previously and the topic we have just finished now. So now let's move on. The first problem: the blood pressure is commonly measured with a cuff placed around the arm. With the cuff pressure, which is a measure of the arterial blood pressure, indicated with a mercury manometer. Okay, so normally we have a device. Whenever we visit the doctor, we see the device he has. Okay, so we see there is a YouTube manometer and the mercury deflects ups and down. Okay, so what exactly happens? A typical value for the maximum value of blood pressure, systolic pressure, is 120 millimeter Hg. That is, we call a high pressure, and the low pressure normally we observe 90 millimeter Hg or 80 millimeter Hg. Okay, for the higher side is normally we say the 120 millimeter Hg is the comfortable pressure for a human body. So why wouldn't be simpler and cheaper to use water in the manometer rather than mercury? We know the mercury is an expensive material, so instead of that we use a water based pressure measuring device. Don't you think it's going to be more cheaper and easier to use it? So explain and support your answer with the necessary calculation. So why don't we use water instead of mercury? That we have to explain. So let's see how we can do that. So here previously we have derived the equation P is equals to rho gh, or P is equals to gamma h. H is the height of the column. So in the equation it is given the height, this is the height of the column given, and by using this, because this is the mercury of Hg and this is the weight density of the mercury, okay, that you can get it from the table, okay, that I will post in the Google Classroom, okay, where you can see the properties of the other fluids as well. So here is the weight density of the mercury, and H is the height of the column. So you have to convert, because this is an SI unit, so this is in millimeter of Hg, the CGS system or something. So you can convert it into SI system. So this is going to be 0.12 and you convert it into 16 kilopascal. So the same pressure, we can see what height of the column you will get, okay, to achieve same pressure by using water. So let's see, P is equals to gamma H. So P is equals to gamma H, separate H to P over gamma. So the specific weight of the fluid, or that is 9.8 into 10 to the power 3, okay, that is 1000 into 9.8, okay, that is basically rho g, the density of water into gravitational acceleration. And this is the pressure, the same pressure we want to see what height of the column we can get. So if you divide this pressure with the density of water, what you will get, that is 1.63 meter. So normally you see we have the pressure measuring device is almost 15 to 20 centimeter long or 25 centimeter long, but here see the height of the column we needed for this pressure 1.63 meter, almost 2 meter, okay. So how it is possible to carry such device, such a big device, okay. So therefore if water were used in manometer, the required column height would be too high and impractical. Therefore this is the reason we cannot use water in the blood pressure measuring device, because the deflection is too high. Now let's move on to the another question. So develop an expression for the pressure variation in a liquid in which the specific weight increases with depth, okay. That means the density of the fluid is varying with respect to height. We have discussed 4 or 5 cases during the derivation of hydrostatic equation of the fluid, okay. So this is one of the case, okay, and this variation of specific weight following a equation, that is gamma is equals to kh plus gamma naught, where k is a constant and gamma naught is the specific weight at the free surface. Free surface is a surface where there is no shear stress, only a normal stress or normal pressure acting on it, and that pressure is basically atmospheric pressure. The surface which is open to atmosphere is called free surface. So let's see here. So this is the free surface where the specific weight of the fluid is gamma naught as it is given here, and consider at height h, the specific gravity of the fluid is gamma, okay. The total height from here to here is z naught, and the point we are saying, because since the specific weight of the fluid is varying with respect to height, so at height h the specific weight of the fluid is gamma. Maybe if you come further down, the specific weight will gamma 1, gamma 2, gamma 3, because the specific weight is the function of height. As the height is changing, the specific weight of the fluid is also changing. So now we know that the dp over dz is equals to minus gamma, okay. This is the equation we derive, okay. So since we have to develop an equation for the pressure variation with respect to height. So we know this is the equation, dp over dz is equals to minus gamma. So h is equals to z naught minus z, and dH is equals to minus, if you take the derivative, so dH is equals to minus dz. Okay, so replace here, replace dP is equals to dz is equals to dH. So we replace dz is equals to dH. So minus and minus going to be plus. So here then take the integration 0 to, the pressure is here and the free surface is 0, because as the fluid pressure, as the fluid depth increases, the pressure increases. Okay, so from 0 to P, and at 0, and the pressure at 0 height is 0, and the pressure at h height from here to here is h is equals to P. Since gamma is not constant, it is variable, so we cannot take it out, so we are taking it as a function. So we replace gamma with a given function kh plus gamma naught, and then we took the integration, and finally we end up with the equation pressure is depending on height h, okay, when the fluid has a specific weight varying. Okay, so based on that we can calculate the pressure. So if the density is constant, then what equation we can use? Straight away we can use P is equals to rho gh. Okay, this is the basic equation. We don't need to follow this equation if the weight density or density of the fluid is constant. So P is equals to gamma h. Straight away we can use from here to measuring the pressure. But since the density is increasing, the specific weight is increasing, so we cannot use that equation. So this equation will be applicable for that. Okay. Now this is the problem for the manometric device. So here what is the problem? A closed cylindrical tank filled with the water has hemispherical dome, and it is connected with an inverted piping system as shown in the figure. The liquid in the top part of the piping system has a specific gravity 0.8. The specific gravity here in the pipe, that is also called a manometric fluid. We can manometric fluid, that is 0.8, and the remaining part of the system are filled with water. If the pressure gauge reading at A is 60 kilopascal, the pressure we are seeing here is 60 kilopascal, determine number A. The pressure in pipe B, we have to find out the pressure. Consider this is a container, okay, and this is a pipe passing through in this line, and a small pipe is connected with it to measure the pressure. So the pressure in pipe B, so this is the pipe B, okay, and the pressure head in millimeters of mercury, that means in the height of the column, at the top of the dome point C, and we have to measure the pressure at point C as well. Okay, so two things we have to do: one, we have to measure the pressure at point B, another to measure the pressure at point C. So let's move on to what exactly we have to do first. So to solve the manometric problems, what I told you, to see, first of all, make a datum line. Okay, so how we can do that, and then we can see what are the things are given and what are the things we have to find out. So what are the things are given to us? The specific gravity of the fluid is given, okay, all the heights are given, the pressure at point P is given, okay, and distance from point C, because the pressure at every point on this horizontal plane is same, okay, according to the Pascal law. The pressure at point, this is point A, is 60 Pascal. So here is also 60 kilopascal, here is also 60 kilopascal, here is also 60 kilopascal, here is also 60 kilopascal. At every point on this plane the pressure is same, it doesn't change. So from here to here, okay, what is the height? Is 3 meter. So here is 60 kilopascal, and we have to find the pressure at point C, and these are the fluid. What is the fluid? Is water, and we know the specific weight of the water, so most of the things are known. So let's use the equation. So consider this line as a datum line, okay. And now what I told you before, how we can measure the pressure. So the pressure at this point and pressure at this point is same. So we have to measure the pressure at this point and we have to measure the pressure at this point, okay. So how we can do that? So you can see, so pressure at this side is equal to pressure at this side. So we start from here. So what is the pressure at this point? At this point we can, as I told you before, because this is a continuous fluid, this is the continuous fluid, whatever is the pressure here, the same pressure is applying here, okay. That we have previously discussed. So the 60 kilopascal is the pressure at this point. So here is the pressure is 60 kilopascal equals, what is the pressure here? PB. And then from PB we are going up. When we go up, the pressure decreases. So PB minus what is the gamma into 2 meter, gamma of water into 2 meter. Then we are further going up. What is the specific weight of the fluid? Is 0.8 into the specific weight of the 0.8 into specific weight of the water into G into H. So this is 0.8 into 9.8 into 1000 multiplied by 3 meter. So yani gamma of this specific gravity, gamma of water into this height, okay. So let's see, you see the pressure PA, if I make equation like this, PA equals PB minus what? This is the water, specific weight of water into 2 meter height that I showed to you previously, specific weight of water into 2 meter height, and then 3 meter into 0.8 into specific weight of water, okay. So this is okay, because this is the minus, both are going up, so minus minus, so when we take it other side it become plus, okay, it become plus. So this is how we measure the how we make the equation. When we simplify this, you will end up with PB is equals to 103 kilopascal, okay. Now the second part of the question is to the pressure head in millimeters of mercury at the top of the dome. So we have to find out the pressure at this point, okay. So here we can see there is no height of the column, okay, there is no height of the column. So this is the pressure due to the pressure of the pressure exerted on the surface of the container by the fluid. This is not due to the weight of the fluid, this is due to the force exerted by the fluid particles. So how we can measure it? From here to, we know the pressure at this point. So if we minus this height of the column, if we minus the pressure due to this weight of the fluid, so we can get the pressure here, okay. That means PA, that means PC is equals to PA minus this pressure due to this height of the column of the fluid. So that means PC is equals to PA minus what is this? Water, gamma water into 3. So let's see here, PC is equals to PA minus gamma H2O into 3. So when you simplify it, you will end up 30.6 kilopascal Newton per meter square. But you have to change this pressure in millimeter of height of the column. So what is the formula? H is equals to PC over gamma H, and P is equals to rho gamma into H. So H is equals to PC over gamma. You end up with 0.323 meter. And then you know 1 meter is equals to 1000 millimeter. You multiplied it, then finally we end up with 230 millimeter of H2O. So this is the solution. So now let's move on to the another inverted U-tube manometer, that is basically measuring the pressure difference between the two pipes. So for the stationary fluid shown in the figure, the pressure at point B is 20 kilopascal greater than the point A. Okay, this is the point A and this is point B, and the pressure in point A is greater than 20 kilopascal greater than point B. Okay, so determine the specific weight of the manometric fluid. So we have to find out the specific weight of this manometric fluid, which is in the gray color. Okay, so first of all, what we do normally, we make the manometric equation. Okay, we make the manometric equation. So how we can make the manometric equation? So you can see the pressure at this point and pressure at this point is same. We can also make it the pressure at this point and pressure at this point is same. So I take the datum here. Okay, I take the datum here, or we can take the datum here as well. There is no problem, it's up to you. Okay, whatever the datum you are taking, normally we take the datum from that point, everything is known. Okay, so let's move. I am considering datum at this point. Okay, so if the datum at this point, that means pressure here and the pressure here is same. So let's see how we can make the equation. So from here, okay, I consider pressure on this side and pressure on this side. Okay, so here PA, we are going up, that means pressure from here to here is 2 meter. So what is the specific weight of the fluid is 1.2. that means the specific weight of the fluid is known, specific gravity is known. 1.2 into specific weight of water into G will give you the specific weight of the fluid, specific weight of the given fluid. So that means gamma of this fluid into 2 meter height will give you the pressure here. Yani PA, we are going up minus, okay, of this, and then you are here. Then start from here. PB, you are going up minus density is given, density into G into 2 meter height. Then from here to here. So what is that? This is basically the manometric fluid. To consider, this is gamma m into height 2 meter. Okay, so this will give you the equation. So let's move on. You see, gamma m is the specific weight of the manometric fluid. Then they calculated gamma a. Gamma a what? Specific gravity, which is given. Gamma of water into G will give you the gamma a. Gamma b, density was given, you multiplied with G and then you got it the value of gamma b. So now you made the equation PB minus gamma b into 2m, because if you take it minus here, because I started the way what? I started this way. Yani PB, sorry, this is PB, and then you move up minus gamma b into 2. Let's see here. If you go PB, this is gamma b into 2. If you take it this side, so PB minus gamma b into 2 equals then PA, then minus gamma this, and then manometric fluid of this side. Okay, so this is how the equation we make, and then you insert all the value, and finally we end up with gamma m is equals to 7100 Newton per meter cube is the unit of the specific weight, specific density of the fluid. So now there is another manometric problem, because there are so many, this is a big topic, so that's why we are solving there too many problems, so that you can understand how we make the equation for the manometer by using the manometers. So here in the problem, the mercury manometers of figure 2.3 indicates a differential reading of 0.3 meter when the pressure in pipe A is 30 millimeter Hg of vacuum. Okay, so we are seeing the differential. This is the level is balanced up to this point, and this is the manometric fluid, and the differential is 0.3 meter. Since the pressure in pipe A is vacuum, as it is mentioned here, 30 millimeter of Hg, because of the vacuum, the height of the column is going up. If it is pressurized, if it is positive pressure, it must go down. But since the vacuum pressure, because of that, it's sucking the manometric fluid. So here we have to determine the pressure in pipe B. So first of all, basically we see or we make a data that what are the informations are given and what are the things that we have to find out. So here you see it is the water is given and here the oil is given. For the oil we do not have the specific gravity here. Do we have a specific gravity? Is it given? Since the specific gravity of the fluids are not given, the mercury and the water and the oil are not given, so we will take from the table. So now next step is to make the equation for this manometric fluid. So what I do, I consider the datum line on this point. Okay, I consider datum line on this point. Now let's make the equation. So what I told you, so we make the pressure, we make the equation for this line equals to equation for this line. Okay, we will start from here. So pressure PA, and then we are going down, so that definitely is going to be plus. So PA plus gamma of H2O into 0.15 plus gamma of mercury into 0.3 equals PB, and then because pressure at this point and pressure at this point is same, because this will cancel with to each other. So PB, and then we are going down. Okay, so what is the height? The density, the specific weight of oil into 0.15 plus 0.3. So how this equation will balance? To PA, okay, so the PA is given, okay, but it is 30 millimeter of Hg. We have to convert into height of the column, that is in meter of Hg. Okay, we have to convert into millimeter of Hg, or you have to convert into millimeter of meter of water, or you have to convert into pressure. It is better to convert into pressure, PA. Okay, convert into pressure in PA and then put the value here. Okay, so the PA is given but the value is negative. Okay, the PA, since vacuum, so when you will insert the value, let's move on. So PB is equals to PB plus plus gamma oil plus UC, as I told you, PB plus gamma of oil into 0.15 into 0.3, PB plus gamma of oil into 0.15 plus 0.3 equals PA, we all going down here. Okay, PA plus 0.15 gamma H2O. So let's see, plus if you bring this side to gamma H2O plus 0.15 and gamma Hg into 0.3. So PA is known, so we have to find out PB. So you shift all the values there. You see PA is equals to gamma of Hg 0.003. That is given, so it is minus. So you can replace PA by putting this value and convert this millimeter of Hg in meter of Hg you inserted here. So when you simplify it, you will end up with the pressure 33.4 kilopascal. Okay, now this is the last problem, the inclined manometer. So how do we measure the pressure? By using the inclined manometer, and we measure a very slight pressure change due to this manometer. So for the inclined tube manometer, as shown in the figure, the pressure in pipe A is 0.6 psi. Here you see the units are changed. We are dealing with the English system. 0.6 psi. The fluid in both pipes A and B is water, and the gauge fluid in the manometer has a specific gravity is 2.6. You see the gauge fluid is very heavy. Its specific gravity is 2.6, but it's not that heavy than mercury, because mercury is 13 point something the specific gravity. So what is the pressure in pipe B? So we have to find out the pressure in pipe B corresponding to the differential reading shown. So we have to find out the pressure. So as the differential readings are shown here. So here first of all, what we will do, we will make the manometric equation. So we will consider this is my datum line. Okay, this is my datum line. The datum line we consider, from there all the dimensions are known. So from here, so we make the equation. This is the datum line. Pressure at this point and pressure at this point must be balanced. Okay, so we make the equation for this side. PA plus, this is the height of the column, that is 3 inches, into gamma of H2O. Okay, equals, so let's see here, PA plus gamma of H2O. Since this is 3 inches, so we have to convert into feet. Okay, so you have to convert into feet. This is 3 divided by 12. Okay, so here 3 divided by 12 is a gamma into H2O. Okay, so you will use not 1000, you will use the value of H2O. This is the value you will use in the equation. Okay, so from the table you can use for the FPS system what is the value of H, that you can use it, and then move on to PB. So what here is the PB, and then what is next? We are going down. Okay, PB minus, this is vertical height. We do not take a slant height, we will always take a vertical height. So vertical height is 3 inches. PB, okay, PB minus gamma of Hg, so gamma into 3 by 12. So let's move on. This is PB, or you can see gamma H2O into 3 by 12. So here PB, and since we are going down, this is going to be positive, and this is also be positive. So PB plus this value into this height plus this height. The vertical height is not known, but we have slant height is known, that is 8 inches. So we need this vertical height. So this vertical height will be equal to 8 into sine theta. 8 into sine 30 degree will be this. So specific gravity into specific weight of water into this height. 8 inches divided by 12 multiplied by sine theta will give you the equation. This value will be balanced with this value. Okay, so finally we end up with this equation. When you will simplify it, so finally you will got this 0.224 psi. Okay, so this is the end of today's lecture.